All right, in this video we're going to look at an example of finding limits just from the equation. So we've talked about other methods using a table or using a graph to find limits, and those can work too. But just wanted to give an example of doing this from the equation. All right, so I have four limits up here that we're being asked to find. So these two, we're asking us about what happens to the function as x approaches -1 or x approaches +1. And the first thing I would think about is that the domain of this function does not include x equals +1 or x equals -1. I can't just put in x equals -1 or x equals +1 because that would make the denominator 0. So that's the first thing I would notice, and of course that's why we use limits, is often to describe things about functions when they're doing something weird, like they have a problem with the domain. All right, but I would also notice that this particular function can be rewritten. If you remember some factoring, then maybe you realize that you can rewrite this function. The denominator is a difference of squares. So difference because of the minus sign, squares because both terms are perfect squares. And so remembering back from some algebra that difference of squares can be factored into two factors that look almost the same, except one is plus and one is minus. And they're the two factors that would multiply together, if you FOILed that out, to get x squared minus 1. So first terms would have to multiply to give you x squared. Last terms would have to multiply to give you -1, and then you would need those middle terms, a minus 1x and a plus 1x, to cancel out. So recognizing that that denominator factors is helpful, because then if you notice that the numerator is really just a single factor, I don't really need parentheses there, but I went ahead and put them there just to remind myself I'm treating that as a whole group, that I can rewrite this function with these factors canceled. It's not the same function, it's a slightly different function. I'm going to go ahead and write equals here, but with a little qualifier out to the side here. So if I cancel these, I'm left with 1 over x minus 1. Notice the domain of this new function is different than the domain of the original function. So it is this function everywhere except at this place that I canceled out the issue with. So except at x equal -1. So it is equal to this except when x is equal to -1. All right, so I'm actually going to end up working with this function instead of the original function. So sometimes it's advantageous to recognize that you can do a little bit of simplifying. So I'm actually going to do all of these problems really working with this version of the function. All right, so for these two, when I'm letting x approach a number, I need to think a little bit about what's going to happen on either side of that number. So when x is getting close to -1 on one side and when x is getting close to -1 on the other side. So I'm going to do a little scratch work in below here. And of course, you can use a table to help you with this, or you can use a graph as well. But all right, so this first part that I've written here, I'm taking the limit as x approaches -1 from the left. So I'm thinking about that I'm putting in numbers that are very close to -1, but just a little bit less than -1. So I'm thinking about putting in numbers, and if you did a table, you might put in numbers that are just a little bit left of -1, like -1.1, -1.01, etc. And you could certainly do that on a table. But thinking about what's going to happen here as I put in numbers that are, I'm just going to write some words here, 1 over numbers that are close to -1, but a little less. So on the negative side, so a little bit left of -1. All right, so I'm thinking about putting that in for x, and then I'm going to subtract 1 on the denominator. So this is going to be close to -1, and then I'm going to subtract 1. So that denominator is going to be close to -2. Close to -1 minus 1, be close to -2. So 1 over something close to -2, but a little left, since I'm taking a number a little bit left of -1 and then subtracting 1. All right, so this is not nice mathematical notation. I just wrote some words here to describe what's happening, but this limit here, I'm going to get a denominator that's close to -2 and 1 over that. So this limit really would be -1/2 as x approaches -1 from the left. I'm going to do the same thing here when I think about putting in numbers that are close to -1, but a little bit right of -1. So like -0.99. Sometimes students have a hard time with the numbers there, but just I kind of visualize a number line, -0.99, for example. So you could certainly get out a calculator and do that. If you plug in a number close to -1 but to the right and then subtract 1, you're going to get a number that is close to -2 on the denominator, but a little bit right of -2, so maybe -1.999. And again, that's getting closer and closer to -2, so this limit is -1/2 as well. And since these both agree, we would say that this overall limit is -1/2 as well. All right, so I did not make a table, but I mentioned a table a couple of times on something that's important like a test. It might be worth verifying. So doing it one way and then verifying by using a table to make sure that you're getting those same values. If it's just homework, you might just think it through and try it, and your homework's going to tell you whether you did it right or wrong, and you can get another attempt if you want to. So maybe not a big deal on the homework, but certainly on a test where you want to make sure you get that problem correct, you might just verify by using a table. All right, this next one, we might notice that when I plug in numbers here, when I think about numbers close to +1 but right, I'm going to get a number that is close to 1 but a little bit right. So a little bit bigger than 1, so like 1.01, and then I'm going to subtract 1. All right, so that denominator is going to be very close to 0, not equal to 0, but it's going to be a little bit bigger than 0. I'm plugging in numbers a little bit bigger than 1 here, and then subtracting 1. So close to 0, but a little bit right of 0, a little bit bigger than 0. So close to 0, but a little bit bigger than 0. And so thinking about what happens when you have a fraction where the numerator is fixed, 1 in this case, and the denominator is getting smaller and smaller and smaller and smaller. And since it's a little bit bigger than 0, that's going to mean the denominator here is positive, a little bit bigger than 0. So 1 over a number that's getting smaller and smaller and smaller, but positive, closer and closer and closer to 0, the value of this fraction overall is going to get larger and larger and larger. And so this fraction is approaching positive infinity. When I am plugging in numbers a little bit bigger than 1, I'll get larger and larger and larger outputs for that function. All right, what about when I plug in numbers that are a little bit smaller than 1? So close to 1, but left. So 1 over something that's close to 1, but a little bit left. So a little bit less than 1. All right, so a little bit less than 1, so maybe like 0.9 or 0.99. And then think about subtracting 1. So if I take 0.9, for example, and I subtract 1, I'm going to get a number that is close to 0, but negative. Or a little bit left of 0 if you want to talk about left and right. So 1 over some number that's close to 0, but negative, left of 0. And so in the same way that we thought about this, the value of this fraction, numerator was fixed, denominator was getting smaller and smaller and smaller. But in the previous one, everything was positive. So we got larger and larger size, but positive. Here I'll have a positive numerator and a negative denominator. So positive over negative, I'll get numbers that are large in size but negative. So negative infinity. All right, so these two are not the same. Positive infinity, negative infinity, these two are not the same. The one-sided limits do have answers, positive infinity or negative infinity, but the overall limit, we would say, does not exist because these two are different. They don't agree. All right, so let's look at these last couple over here that are asking us about what happens when x gets larger in size, positive or negative. All right, so again, you can get out your calculator and plug in some numbers if you want. Sometimes that takes a long time, and the better you get at these, the more you're able to kind of think about what's happening without necessarily needing to plug in numbers, but that's always an option. All right, so when I plug in numbers that are larger and larger and larger, positive, I'm going to get values that are 1 over some very large positive number. All the large positive numbers, bigger and bigger and bigger, and then subtract 1, I'm still going to have a very large positive number on the denominator. And so if you think about a fraction where the numerator is fixed and the denominator is getting larger and larger and larger positive, so 1 over a million, 1 over a billion, 1 over a trillion, the value of those fractions are getting closer and closer to 0. Right? 1 over some very large number makes the overall fraction closer and closer and closer to 0. So the function value won't equal 0, but it is getting closer to 0. It'll actually be a little bit bigger than 0, but 0. All right, so 0 is the answer of that. And you don't need to write the plus there necessarily. Sometimes it's helpful to know that it's actually going to be a little bit bigger than 0, in the same way that we use the plus and the minus to show bigger or smaller here. All right, and then on this one, we are going to have 1 over numbers that are large in size but negative. So large size but negative numbers minus 1. So negative a million, negative a billion, negative a trillion minus 1 is going to give you a very large in size denominator, negative. So a positive over a negative will be a negative, but the size of that overall fraction is just going to get closer and closer and closer to 0. So just think about 1 over negative 10 million, 1 over negative 10 billion, right? So that's negative, but very, very close to 0. So this limit is 0, and maybe you want to say it's approaching 0 from values slightly less than 0, negative. Most of the time our homework just will want you to give 0 here. They won't necessarily want you to put the plus or minus there. All right, so thinking about from equations, the big key thing I wanted to emphasize here was if you can simplify the equation first, go ahead and do that. Sometimes that makes your work easier. And then you're really just thinking about large in size numbers or numbers that are close to other numbers or whatever. And that you can always use a graph or a table to help verify these answers that you've gotten.